The MSPM0-C1104 LaunchPad development kit is an easy-to-use evaluation module for the MSPM0-C1104 microcontroller. The kit includes everything needed to get started with development, including an integrated debug probe for programming and debugging. The board also features a button and an LED for quick integration into your own projects. The MSPM0-C1104 is a 32-bit Arm Cortex-M0 plus CPU with a frequency of up to 24 MHz. The device includes 16 kilobytes of built-in flash memory and 1 kilobyte of built-in RAM. This device features a 12-bit 866 kilosamples per second SAR analog to digital converter with 10 channels. The 20-pin booster pack plug-in module headers simplify rapid prototyping. Users can quickly add additional features such as wireless connectivity, graphic displays, environmental sensing, and much more. First, download and install a development environment. The official one is CCS, Code Composer Studio, currently downloadable from link you can find in the description. Click on the download options and select the correct operating system. Now let's launch the development environment and create a new project. The software will ask for the device connected to the USB port. Type the string 1104 and you'll see the name of the board and the MCU mounted on it. Select MSPM0-C1104 LaunchPad. Then select No RTOS as the kernel and the CSS TI-ARM Clang compiler as the compiler. As a basic example, select GPIO toggle output. The default firmware will be replaced with our own. Click the Create button and confirm the selection of MSPM0-C1104. A progress bar at the top confirms the ongoing operation. At this point, the development environment displays some features of the microcontroller. Of particular interest is the right-hand section listing the available and occupied I/O ports. Now double-click the source file with the .c extension. Delete all its content and replace it with the code shown on screen. Pay special attention to the delay value, which in this case corresponds to a half-second pause. Go to the project menu and select Build All. The system will take a few seconds to compile your firmware. When the compilation is complete, go to the Run menu and then flash a project. This phase mainly serves to load the binary files into the microcontroller. Again, wait a few seconds. Let's very briefly examine the source code used to make the onboard LED blink. It's very simple. This line includes TI's configurations and libraries for the MSPM0 board. This line defines a 0.5 second delay for a 24 MHz clock. This function initializes the GPIO pins as digital ports. This function initially turns off the LED inside the infinite while loop. This function turns off the LED. This function causes a half-second delay. This function turns on the LED. This function again causes a half-second delay. An important info, the LED is connected in an inverted logic configuration. It turns on with a low level, so clear pins turns it on and the set pins turns it off. As shown in the images, the LED blinks at a frequency of 1 Hz. This is always the starting point for building more complex projects. This kind of application is useful for getting familiar with configuring GPIO operating modes, using variables, infinite and conditional loops, and delay functions. According to the official schematic of the MSPM0-C1104, the cathode of LED1 is connected to I/O port PA22A4 through resistor R4, while its anode is directly connected to the 3.3 volt supply. This is why when the logic level on this port is high, the LED is off, and vice versa. The device provides a header connected to the communication ports of the microcontroller. It can interface with any actuator or sensor. Using small jumper wires, we connected the port PA22A4 to the probe tip of an oscilloscope and GND to the oscilloscope's ground. On the screen, you can observe alternating 1 and 0 generated by the microcontroller in opposite phase with the LED's logic state. The next example involves controlling the brightness of two high-power lamps, drawing at least 8 amps using PWM. The microcontroller sends a variable pulse train to the MOSFET gates, adjusting the lamp's brightness. But the logic system and power system use different voltage levels. One runs at 3.3 volts, the other at 12 volts. A circuit is needed to adapt these voltage levels to allow proper communication between them. We built this simple level shifter to adapt the microcontroller's 3.3 volt signal to the 12 volt level required to drive the MOSFET gates. This allows the two units to interface without any issues. The system is now operating. Brightness gradually decreases due to the decreasing duty cycle of the PWM signal set here to 100 Hz. You can observe the narrowing rectangular signal directly on the oscilloscope. The cycle repeats indefinitely.